So what I want to do today is I want to talk about analytic continuation of the Riemann zeta function. So we've only talked about the Riemann zeta function when the real part of s is greater than 1. What is the big property the Riemann zeta function has that we care about so much? Yes, the Euler product. So at some point in our investigations, the Euler product is going to have to play a major role. So we want to do the analytic continuation of zeta of s. There's a lot of ways to do this. There's good ways and less good ways. I'm not an English professor, so I can say things like less good. Okay? Ideally, we would love to do to the Riemann zeta function what we did to the gamma function. When we analytically continued the gamma function, we got a functional equation, and from that functional equation, we then had its value everywhere. That was wonderful. We did that with the geometric series. We got a functional, well, okay, we just analytically continued the geometric series. It was just so easy. And we had a value for all values of s. What we can do is we can do something very similar to the Riemann zeta function. We can develop a functional equation for the Riemann zeta function so that we can continue it everywhere. For many purposes, we don't need to do that. We'll see later that the action for the Riemann zeta function occurs between 0 and 1. And in fact, the famous Riemann hypothesis is, this is not horrible because it's prime of the line 1/2. The famous Riemann hypothesis is all the non-trivial zeros of the Riemann zeta function lie symmetrically on this line. The other zeros, -2, -4, -6, are all at the negative even integers. The negative even integers are very well understood. It's conjectured that all the non-trivial zeros of the Riemann zeta function have real part 1/2. This is the Riemann hypothesis. This has enormous consequences in the distribution of properties of prime numbers. The point of this is that the most important region to understand the Riemann zeta function is for s between 0 and 1. That's where the action lies. So rather than continuing the zeta function to the entire complex plane, it would be nice if we could continue it just to the real part of s greater than 0. Now, when we had the gamma function, we had this wonderful integral representation for it. Did that integral representation work when the real part of s was, say, -6.3? No, we lost the integral representation for -s. So it would be nice if when we analytically continue the Riemann zeta function, that whatever we continue it to has a nice formula to work with. Right? It's not enough to just have an expression that exists. We want an expression that's tractable. So we're going to first do the alternating approach. And this is hopefully something you've seen in other classes. So zeta of s is defined as 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, plus 1 over 5 to the s. How much do we have to fill up with? So there's the Riemann zeta function. I'm now going to multiply by 2 over 2 to the s. So if I just multiplied by 2 to the s, by 1 over 2 to the s, what would I do? I would have 1 over 2 to the s, 1 over 4 to the s, 1 over 6 to the s, 1 over 8 to the s, 1 over 10 to the s. So if I just multiply by 1 over 2 to the s, I now just have the even terms of the zeta function. Because I'm multiplying by 2, I now get twice all the even terms. And I'll put a negative sign. So we'll get a negative 1 over 2 to the s, minus 1 over 4 to the s, minus dot, 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 dot. And so now if we add, or I guess subtract, well, they both have a zeta of s, so you get 1 minus 2 over 2 to the s times zeta of s is 1. Oh, so they should all have 2's. So now when we subtract, we get 1. We have a 1 over 2 to the s, a negative 2 over 2 to the s. We get a minus 1 over 2 to the s, plus 1 over 3 to the s, minus 1 over 4 to the s, plus 1 over 5 to the s, minus. And this function is given the name eta of s. So 1 minus 2 to the 1 minus s, zeta of s. Or, if you can do division, zeta of s is eta of s divided by 1 minus 2 to the 1 minus s. So we've got to be careful. When are we not allowed to divide?
When the denominator is 0.
When the denominator is 0, and when is the denominator 0?
S equals 1.
S equals 1. So you can then try to figure out, is there a pole at s equals 1? What's the residue? Other than that, we're okay so long as eta of s converges. For what values of s will eta of s converge? If you want, just consider s to be a real number at this point. So s real converges if what?
Greater than 0.
Greater than 0. So as long as it's greater than 0, we have an alternating series of decreasing magnitudes. So if you want to just do the running sum, it's 1, then it drops lower, then it rises up, but it can't rise up as much as it fell down. Then it drops down.
Does it mean greater than or equal to 1?
I'm sorry?
Greater than 0?
Greater than 0.
Okay.
Because as long as s is greater than 0, these terms are going to be going to infinity.
Yeah. Right.
Yep. And so it converges if s is greater than 0. As an exercise, you're okay if it's just the real part of s that's greater than 0. And then these become games in partial summation and whatnot. If you want to try to explore that, that's a great problem to do. If you want to do that instead of one of the homework problems I've assigned, absolutely fine. So I'm going to try to do stuff like this throughout the semester, is to give you some choice in what you do. You know, if you want to do the homework problems I've assigned, great. If you'd rather try your hand at something like this, absolutely fine. This will give us an analytic continuation of the Riemann zeta function to the real part of s greater than 0. With a little bit of work, you can show that this has a pole at s equals 1. Does this series converge at s equals 1? Yes. Anybody know what it converges to at s equals 1?
Is it Euler's scaling?
No. Do people want to go through a little detour and see what we get? Let's have some fun. Alright. So, one of the nice things about teaching a class like this is you have lots of different fun things you can do. So, anybody recognize that sum?
Alternating.
Alternating harmonic. What's the alternating harmonic? This is equal to the log of 1 minus negative 1, also known as the log of 2. Got to be a little careful. The log of 1 minus u is negative. Oh, sorry, I want to make sure. I want to make sure I'm doing this correctly. I think it's negative of that. So let me go a little bit carefully. If I do the log of 1 plus, okay, I think I'm off by minus, and we'll find out in just 1 second. No, it should be okay. So the log of 1 plus u is equal to u minus u squared over 2 plus u cubed over 3 minus u to the 4th over 4. And if you take the limit as u goes to 1, this series converges. And will give us the log of 2. So now let's look at 1 minus 2 to the 1 minus s. And we want to take the limit as s goes to 1. Well, we know what that is. What's the limit of this as s goes to 1?
0.
0. So what we want to do is we want to write this as a Taylor series. We want to write it as s minus 1 times something, and then figure out what is the residue of that function. So this is a good way for us to review residues, which is why I don't mind taking a detour like this. So how would we write something like this? Well, you always go back to what do you know. Do we know what the function 2 to the 1 minus s? Do we know its Taylor series expansion? Okay. How do we know its expansion?
We can change the 2 into an e.
Yes. And how do we change it? So 1 minus 2 to the 1 minus s is 1 minus e to the 1 minus s log 2. Ah, okay, the log 2, it's probably going to cancel that log 2. And now if we start to expand, we get 1 minus quantity 1 plus 1 minus s log 2 plus 1 minus s squared log squared of 2 over 2 factorial plus dot dot dot. So now the 1's cancel, the minus signs flips the s to 1 minus s, and we get s minus 1 plus over here, we have a minus sign that flips one of them, we need another minus sign, so it'll be minus s minus 1 squared over 2 factorial log squared of 2. Plus dot 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 dot.
Log out front or not?
Oh yes, and log 2 over here, thank you. Okay, so now what we can do is 1 over 1 minus 2 to the 1 minus s. So let's see how we can write this. We now start at 1 over, we can pull out an s minus 1 log 2, and what will we have? We will have 1 minus s minus 1 log 2 over 2 plus dot 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 dot. So when you look at it, you get a 1 over s minus 1, and you have a 1 over log 2, 1 over 1 minus s minus 1 log 2 over 2 plus dot dot dot. What can you tell me about this piece as s goes to 1? What kind of function is this? So what can you say about this function as s goes to 1? Is this well behaved? Is it not well behaved? It's well behaved. What kind of function is that?
Which goes to 1 over log 2.
Goes to 1 over log 2. This is holomorphic, not 0, not infinity. It's well behaved. So if I want to figure out what's the residue, I want to figure out what is the 1 over s minus 1 coefficient in the Taylor series expansion. One thing I could do is I could take this, use the geometric series expansion, pull that out, start expanding things. But there's no need. Only calculate what you need. We only need the 1 over s. So all of this stuff is fine. So we get the residue at s equals 1 is just going to be 1 over log 2, and then this part is just 1 over 1. So we get a residue of 1 over log 2 from here, but eta, as eta of 1 is log of 2, we get the limit as s goes to 1 from above of zeta of s is going to look like 1 over s minus 1. So it looks like it has a pole of order 1 at s equals 1 with residue 1. So the logs all cancel. If you want, if you can calculate the residue of the zeta function at 1 in an alternate way, you can actually use that to get a formula for the harmonic alternating sum. Right? We use the fact that the harmonic alternating sum is the log of 2 to then get the residue here is 1. You can go backwards. If you have another way of analytically continuing and figuring out what's going on at 1, you can then prove a formula for the harmonic alternating sum. So lots of fun things you can do. There's a great paper that I make a lot of my research students read about what happens if you replace the alternating harmonic sum with a random harmonic sum. So you maybe flip a coin, and then you put pluses and minuses. And there's lots of generalizations you can do. You can ask questions about what happens in these situations. So this is the first cheap analytic continuation of the Riemann zeta function. It gives us a series expansion, it gives us the pole, it gives us the residue at the pole. It is a really nice argument. Okay, any questions about this? I'd like to do another cheap continuation of the Riemann zeta function. There's a significantly better one involving theta functions and a little bit more Fourier series. They talk about this in the book. I think it uses something from chapter 4. I haven't decided yet if I want to go through the details of that in the class, or basically just say, let's just assume the Riemann zeta function satisfies this functional equation. This is not a course in number theory, this is a course in complex analysis which can be used. So either take an analytic number theory course in the future or take one in the past. Alright, so I want to just quickly state the other formula so I don't get this wrong because it would be very bad. Zeta of S is equal to the sum n goes from 1 to infinity of n times 1 over n to the s minus 1 over n plus 1 to the s. Okay. What I like is the proofs we're seeing today highlight some of the most important methods in mathematics. We did before for the alternating series, we did this wonderful like shifted addition which has massive cancellations and got us a new function. So the reason that worked is basically 1 over 2 to the s times the zeta function is also very nice. You might have seen that before, so as an aside, I probably should have said this a few times, but I apologize. Let's say you know the sum n goes from 1 to infinity of 1 over n squared is pi squared over 6. What is the sum n goes from 0 to infinity of 1 over 2n plus 1 squared? I apologize, I probably should have done this before jumping to this, but I want to figure out what's the sum if I just go over the odd terms. Well, we know the sum n even plus the sum n odd, 1 over n squared, 1 over n squared, is pi squared over 6. But if you look at the evens, since I'm squaring everything, it's just 1/4 times the whole thing. So this is just 1/4 the sum all n, 1 over n squared, plus the sum n odd of 1 over n squared is pi squared over 6. Well, we know what this is. This is pi squared over 6. This is the bring it over method. We know that this is pi squared over 6. We have 1/4 of that. We have 4/4 of them over here. So we get the sum n odd of 1 over n squared is going to be, if I've done this correctly, 3 pi squared over 24, or pi squared over 8. Powerful 8. Of 8. So, how many of you have seen this method before? This is extremely powerful. I really want to highlight this. Is you're representing something you know, and you're seeing how that emerges in the problem you're studying. Let's do just one more example of this method. It's so important. What is our favorite sum to sum?
Geometric.
Geometric. So we have 1 plus x squared plus x to the n minus 1 plus x to the n. So we have an infinite sum like this. If we look at just the first terms, this would be the sum n goes from 1 to n minus 1 of x to the n, plus, now over here for all of these terms, I can pull out an x to the n. And now from this point onward, I have 1 plus x squared, and I have an infinite sum. What's so nice about the geometric series is the tail of a geometric series is a geometric series. So tail of a geometric series is a geometric series. What that means is that this is equal to a finite sum. The sum n goes from 1 to n minus 1 of x to the n plus x to the n over 1 minus x. It allows you to replace the infinite sum with a finite sum. If you now want to interchange, say, an integral and a sum, a derivative and a sum, you can do that. And you can take the limit as big n goes to infinity. You can use this to justify term-by-term differentiation and integration of the geometric series. I'm advising a colloquium that will be happening, I want to say November 16th, I hope that's your Monday, Wednesday, or Friday, on the trillionth digit of pi. And things like this are going to be extremely important. So I really want you to see the methods and the techniques, the tools we have in our arsenal. These are things that we keep using again and again and again. That's why I wanted to talk about the alternating series proof. Even though, in terms of actually doing a lot of number theory, it's not going to be useful at all for what we're doing. But it highlights a good idea. Similarly, over here, this is another application of that idea. We take what we want to do, we break it up, and we recognize constituent pieces are nice multiples of the object we know. And the sum over the evens is a nice multiple of the object we know. That's the whole idea behind this. That's the idea behind the alternating series. The next one is going to be another key idea in mathematics. So when you look at this sum, what's the first thing that comes to your mind when you see this sum? What kind of sum does this look like?
Telescoping?
Telescoping, excellent. When you see things that look very similar with a minus sign, it looks like you're going to be marching down the line. Let's just plug in a few values. When n equals 1, we get 1 over 1 to the s minus 1 times 1 over 2 to the s. When we plug in 2, we get 2 1 over 2 to the s minus 2 1 over 3 to the s. When we plug in 3, we get 3 1 over 3 to the s minus 3 1 over 4 to the s. And now we can see we have a 1 over 1 to the s, a minus 1 over 1 to the 2s, a plus 2. So these don't quite fully cancel, but it will give us a 1 over 2 to the s. These don't fully cancel, but it will give us a 1 over 3 to the s. These won't fully cancel, but it will give us a 1 over 4 to the s. So it doesn't fully telescope, which is what you use in which proof? Where do you use telescoping series in a major, major proof? We go way back. I know we use this in Math372 because I require all my students to know the proof of the fundamental theorem of calculus. You use telescoping series to prove the fundamental theorem of calculus. That you have your upper and lower sums. Here are my lower sums, say, here are my upper sums. And what you do is you'll have a sum of like f of xn times 1 over n. And then what you do is you can rate this to f at, say, xn plus 1 minus f of xn, apply the mean value theorem to this, to the antiderivative. And the mean value theorem and the distance between them will give you something exactly like that. Now here, of course, you would have to use special intermediate points. So you use the intermediate point so that when you apply the mean value theorem, and then you show no matter what point C and you choose, this is going to give you, in the limit, the area. And so you apply the mean value theorem. Now you have a telescoping sum, and it will give you big F of 1 minus big F of 0. So your telescoping sums we use to prove the fundamental theorem of calculus. Here, it's not fully telescoping, but it's mostly telescoping. This is just zeta of s. It's the sum n goes from 1 to infinity of 1 over n to the s. Alright, so now we want to write this in a better way. And the theme here is when I give you a function, we want to try to find a convenient representation of that function. A representation we can work with, we can look at, and we can see what the properties are. So when you see 1 over n to the s minus 1 over n plus 1 to the s, what does that look like to you? I did check my notes before lecturing today, but we should be able to do this without my cheating and looking at the notes. Does this look like anything? So I'm evaluating the 1 over s function at n and n plus 1 and subtracting. That looks a lot like an integral. What function would I be integrating to get that? So we want a t to the negative s minus 1 dt. And if I integrate this, the integral of t to the minus s minus 1 dt should be t to the minus s over s. So I should probably put an extra s over here. And oh wait, when I integrate this, it should be a negative s down here. When I evaluate that, we'll flip the bounds of integration. Wonderful. So when you see something like this, you should recognize this as an integral. I'd much rather work with a nice smooth continuous integral than a discrete sum. So we're making great progress. So now we have an integral here. What's nice about this is, notice how we now have not a t to the minus s, but a t to the minus s minus 1. The hope is that this is going to give us some extra convergence. Now unfortunately we also have something large from this. So we're going to do things in stages. So this is s, the sum n goes from 1 to infinity, of the integral from n to n plus 1. And what I'm going to do now is I'm going to write in square brackets, this means the integer part. Because this function n is constant on this region. So no matter what t is going from n to n plus 1, all these t have integer part n. So I can write this as n t to the negative s minus 1 dt. And now I have a bunch of sums from n to n plus 1. Well, what happens if I sum from n to n plus 1 and I let n range from 1 to infinity? What does this become? Looking at just this part, what's that going to become?
Integral from 1 to infinity?
Yeah, the integral from 1 to infinity. So it's s integral from 1 to infinity of the integer part of t, t to the negative s minus 1 dt. Now, I cannot integrate something like this. That's bad. However, I can integrate from 1 to infinity t times t to the negative s minus 1 dt, and just drop the integer part. Can we just drop the integer part? No. However, what can we do?
It's an upper bound.
It would be an upper bound, but we want an analytic continuation, so an upper bound is not going to be good enough. I can't just drop the floor function. I can't just drop that.
Can we add it on later, or subtract it off later?
What do we want to subtract off?
The fraction part.
Yeah, so just subtract off the integral from 1 to infinity, the fractional part, as we often use curly braces like this, the fractional part of t, t to the negative s minus 1 dt. And if we do this, this is now going to be the fractional part. Okay, why is this so useful? Well, let's think about this integral. What do you know about the fractional part of t? What can you tell me about the fractional part of t?
It's between 0 and 1.
It's between 0 and 1. We need both. You know, if the fractional part of t was becoming more and more negative, going off to negative infinity, that could be bad and make this integral diverge. But this is between 0 and 1. This is positive. So the integral is at most t to the negative s minus 1. When we integrate that, we'll get a t to the negative s over s. And there should be an s over here, sorry. So, so in terms of just what the contribution is going to be, that piece is fine. So the integral from 1 to infinity of the fractional part of t, t to the minus s minus 1 dt, is going to be less than equal to the integral from 1 to infinity, and this will be greater than or equal to 0, of t to the negative s minus 1 dt. This is going to be t to the negative s over negative s at 1 and infinity. This is going to be 1 over s. So as long as the real part of s is greater than 0, so when I'm writing this part over here, I'm implicitly assuming that s is real. Otherwise, I would have to just put like the real part of S. So, you know, assuming S is real. The general case is no problem. That means this piece is well behaved. Let's look at the other piece. The other piece is the integral is S times the integral from 1 to infinity of t times t to the negative s minus 1 dt. Well, I have a t to the negative 1, you know, cancel, and you get s times the integral from 1 to infinity of t to the negative s dt. So we have s, and now when we integrate this, t to the negative s becomes t to the negative s plus 1 over negative s plus 1, or 1 minus s, evaluated at 1 and infinity. And so now, when I put in infinity, as long as the real part of s is greater than 0, okay, right. So what I'm going to do right now is I'm going to assume the real part of s is greater than 1. If the real part of s is greater than 1, what happens now when I put in infinity? Well, if the real part of s is greater than 1, the negative s is larger than the 1, and we're fine. If I only assumed the real part of s was greater than 0, I would have trouble. But as long as the real part of s is greater than 1, it exists. And it's going to be 0. And then I plug in t equals 1, and I'm going to have a negative sign, so I'm going to get s over s minus 1. And here's the trick. I first do the integration when the real part of s is greater than 1. This expression now, I can analytically continue. This is one of the easiest analytic continuation problems I can give you. Given the function s over s minus 1, please analytically continue this to a nice function of s. It's s over s minus 1. There's nothing to do. And so this gives us the function zeta of s is s over s minus 1 minus s times the integral from 1 to infinity of the fractional part of t, t to the negative s minus 1 dt, real part of s greater than 0. And so the reason we need the real part of s to be greater than 0 is not because of this piece over here, but because we need this piece over here to be well-defined and bounded. What's the residue of this at s equals 1? Well, this part here is well-behaved. So we just look at the function s over s minus 1. We want to do the Taylor series. If you want, if you want to do ridiculous overkill, and it's okay to do ridiculous overkill at times. So we have s over s minus 1 is s minus 1 plus 1 over s minus 1 is 1 plus 1 over s minus 1. Or if you want, you can write it as s minus 1 inverse plus 1. For the ridiculous overkill, you get that the residue is 1. That now gives us an independent proof of the alternating harmonic. So a lot of great stuff here. Okay. Any questions on what we've done so far? We now have two analytic continuations to the Riemann zeta function. Neither one of them is terrific. But okay. So we've got about 15 minutes left. We're working up to a rough proof of the prime number theorem. And again, this is not a number theory class. I'm trying to just go through the parts that really emphasize good mathematics and show you how the complex analysis we've done is useful. There are two ways to go from this point. I can try to motivate the calculation, or we can do the calculation and see that it's useful. we've done so much today about trying to motivate what we're doing. Let's do the opposite in case we have people who don't like applications. Let's just do an integral. So I want to evaluate the following. Given c is greater than 0, I want to integrate 1 over 2 pi I integral from c minus I times infinity to c plus I times infinity y to the s dy over y. Okay? Oh, so dy over s. Okay? I want to evaluate this integral. And, sorry, ds over s. This is going to be a function of y. So for a fixed value of y, I let s range from c minus I infinity to c plus I infinity. And I get the following. I get 0 if 0 is less than y is less than 1. I get 1/2 if y equals 1. And I get 1 if y is greater than 1. So the question is, how do we evaluate this? We could try to write this in terms of maybe sines and cosines and do this using real analysis. But this is a class in complex analysis. Probably complex analysis is useful. What does this look like over here? So there should be some clues in how this is written as to what theorem we want to use. What theorem do we want to use?
Residue formula.
We probably want to use the residue formula. What's the biggest hint that we want to use the residue formula?
2 pi I.
Yeah, we've got a 2 pi I, a 1 over 2 pi I outside, with an integral following it. Now, if you want to do the residue formula, you want to have an integral over a closed curve. We don't have an integral over a closed curve. What we need to do is we need to close it. And what we want to do is we want to be able to prove that either we can evaluate the integral over the rest of the closing part, or that the integral over the closing part is negligible. So let's look at what's going on. For what values of s am I worried over here? 0. Excellent. Why am I worried at 0?
Because divide by 0.
Yeah, we're dividing by 0. So this has a pole. Excellent. If we want to use the Cauchy, residue theorem, we need poles. So c is going to be some number greater than 0. And here, this is maybe c minus I times r, and here's maybe c plus I times r. And now we've got the function y to the s. So we have two ways to close the integral. We could go like this to the right, or we could go like this to the left. If we go in one direction, we're going to include the pole and pick up something. If we go in the other direction, we won't include any poles. Which one do you think is the way we should go if we want to take the case y is less than 1? Probably this way, since we're getting a 0, so we shouldn't be including the pole. So maybe what we would want to do in that case is take something like this. So and then we have to decide how far we want to go over here. So we'll have a limit as r goes to infinity, and a limit as this goes to infinity. One possibility is we could guess maybe we go to r over here as well. And that could be fine, that they could go to infinity at the same rate. Maybe we want to give ourselves a little bit more freedom and say this is going to some point t. There's no zeros or poles inside. So all we have to do is show the integral over these other pieces are negligible. What's nice is we have a 1 over s, so we have some decay in this as s gets large in absolute value. We also have a y to the s, which is going to become very small as the real part of s grows. So on this part over here, this part's going to be trivial. Right? Let's think about what's going on here. Over here, the real part of s is going to be t, so we're going to have a y to the t, and y is less than 1. Then we're going to be integrating 1 over s. Well, 1 over s has to be at least how large? On this part over here. 1 over s has to be at least how big in absolute value? So,
Just 1 over t.
yeah, 1 over t. So on this thing, it's equal to 1 over t over here. I could use Pythagoras to figure out exactly what is there. I don't want to use Pythagoras to figure out what is over there. You know, this is where you get to the point where you just say it's small, kind of break your hands like that. So on this part, 1 over s in absolute value is less equal to 1 over t. The length of this is at most 2 times t. We have a y to the t over here, so the contribution is less than equal to 2 t times 1 over t times y to the t. And that's going to go to 0 very rapidly. Okay, so this handles that the integral over this will go to 0 as t goes to infinity. And it doesn't matter how high up we go. Or does it? Have we been too fast and cavalier with the math? Is there a mistake on the board?
Well, it should be r and not t for the way.
Yeah, so if we want to say that this is 2t, then we need r equals t. So you do have to be a little bit careful at times to keep track of all the parameters. We could maybe have t different from r, and maybe try to exploit the y to the t over here. So we know that this would be 1 over r. This would become a 1 over r. And because this is less than 1, the y to the t will still kill the 2 to the t. We don't actually have to take t to be r. We could, and things would be a little bit easier. But either way, we're fine. It's good to just be aware of which parameters. It's nice to have free parameters at your disposal that you can adjust as you continue through the problem. And then just see, what do I need? But you know, it's easy when you have all these different parameters. I could have done something to minimize our chance of confusion. I should label this point over here. So this is the point c minus IR. This is the point t minus IR. And this is the point t plus IR. Oh, so did I do it wrong? No, okay. And now you can see, oh, I'm sorry, I did this wrong. This length, I'm sorry, this length is 1 over t. Sorry, I put them in the wrong way. And so it should be 2r times 1 over t. Okay. Now this is important because if r is going to infinity a lot faster than t, we have trouble. Okay, so apologies. Okay, so now that we have this, what should we take t to be?
R?
So yes. Take t equals r, safe. It's now bounded by 2 y to the r, which goes to 0 very rapidly. So we'll take t to be r. Alright, so now we're left with integrating y to the s along these parts over here. I claim that if we do it just on the top, that's fine. We don't have to do the top and the bottom. Okay. This is going to be an extremely important integral. It's going to allow us to detect things. So we want to bound the integral, and now it doesn't really matter which direction I go on the top or the bottom, right? I'm just trying to show it small. I can go in either direction. I'll take the top and I'll go in the other direction just because it's easier for me to remember. So we're going to start off at c plus IR. We're going to go to r plus IR. So we're going to go from c plus IR to r plus IR. And our function is y to the s ds over s.
Are
Well,
we
we-
still taking t equals r?
We're still taking t equals r.
Okay, because I was wondering
Yes.
where the T was.
Yes, no. We've got to keep t equals r now for the whole thing, because that's what we've said we want there. Well, let's write s. What's a good way to write s? Let's write s as x plus I times r. And now that integral will be the integral x is going to go from c to r of y to the x plus I r. What is ds going to be? That's just going to be dx, and s is going to be x plus I r. And if we take absolute values, if we bring the absolute value inside, it's going to be the integral x goes from c to r of y to the x, because y to the IR has absolute value 1. Y to the IR is just e to the IR log y. And so it will have absolute value 1. So we'll get y to the x dx over the square root of x squared plus r squared. And so now we want to calculate what is this integral. So we need this integral to get small. Right? So let's think about what we have at our disposal. Where do we have to k? Where do we have to k in this? We've got decay in many different places. We need to exploit it. This is how an analyst thinks. Where is my decay?
Got the r squared.
We've got the r squared down here. So this geometry is like a 1 over r. Unfortunately, the length is also the order r. So that length cancels this. So this quantity down here, because x goes from c to r, we're never going to really gain anything from this. Right? There's no hope in trying to exploit what's going on here. Okay, this is extremely important. If x is as small as possible, we get 1 over r. If x is as large as possible, we get the square root of r squared plus r squared. We get 1 over square root of 2r. We're only gaining a constant factor. So if we try to exploit this, we're going to lose. So we can just say that this is less than or equal to 1 over square root 1 over r. You just take the largest value of this, because we're not going to gain anything from that. The integral x goes from c to r of y to the x dx. And this is what I want you to get a sense of, as to how you would try to attack and approach problems like this. You know, where do we have something that we can exploit? Where do we have something we can work with? Okay? So now we have a 1 over r, integral x goes from c to r. How should I write y to the x? We don't like writing things like y to the x. We've done this earlier today with the alternating series. This is a unified lecture, prepared very carefully in the 2 minutes before class. Where have we seen something y to the x? We don't want to integrate y to the x. What do you want to integrate? E to the x. So I should write y to the x as e to the x log y, log of y dx, and I put a 1 over log of y over here. And now I can just integrate this directly. Right? So if I now do this, I get 1 over r log y. The integral of e to the x log y dy, this will be e to the x log y evaluated at c and r. So this is 1 over r log y. When I put in r, I get, well, this is just a function y to the x. So we get y to the r minus y to the c. And because y is less than 1, this quantity here is less than 1. So this is less than equal to 1 over r log y as the absolute value of y is less than 1. There are other tricks we could have potentially done, maybe integrate from c to square root of r, play games like that. There was no need. We were able to find a nice bounding function. And what this now does is we can now just pick up the pieces. This would be a good place to stop. The contribution over here and here and here in the limit goes to 0. So no contribution in limit, no contribution in limit. As the whole integral is 0, sum of residues is 0. This proves the first part. Okay? I will leave the other two as exercises. So if you would like to replace one of the homework problems with the other two cases, that's absolutely fine. In the second case, you'll be going through this way. The case when y equals 1 is a little bit more interesting. And you're trying to figure out exactly what's going on in that case. It's enough to just do the third part. Okay, so this is a good place to stop. We will do a little bit more with numbers.